All right, so welcome to the Spack tutorial segment of the workshop. I'm Todd Gamblin. I'm from Lawrence Livermore. I'm the guy who made Spack originally. It's made by a lot more people now, and we're pretty excited to teach you all about the tool. There's an envelope going around, and I wanted to start by just pointing everyone to where the tutorial materials are. The envelope has logins for Amazon VMs that we are going to use for the tutorial. So everyone should get one. Envelope's right there right now. So if it comes to you, just take one and pass it on. All the materials for this tutorial are online. So you can actually, if you want to, there's a container that you can use to do the tutorial. It's exactly the same as the VM. The details on that are here. Or if you just want to keep it simple, use the VM that we're handing out. But if you do want to follow along, yeah?
Can I just pull down the VM?
It's an AWS VM. There's no image for it right now. Yeah, you can pull down the container. So yeah, if you go to bit.ly/Spack tutorial, all the scripts and presentation materials are there. So you can find a copy of these slides, as well as all of the exercises that we're going to do. And so you can follow along there if you get behind, or if you just want to redo parts of what we've done. The Spack GitHub repository, we'll cover that later, is at github.com/spack/spack. And the documentation is at spack.readthedocs.io. And feel free to tweet at us during the tutorial. We'll be checking Twitter. So the presenters for today are myself and Greg Becker. Greg Becker is not here yet. He's finding parking. But he's also at Livermore. He's a developer on the Spack project. He's implemented a lot of core features. So we're both, we're both heavily involved with the project. All right. So before we get started, I wanted to start with some background. And we talked about this a little bit with the ECP presentation, but software complexity in HPC is growing. And so if you think about even a simple code, this is Nalu from Sandia National Lab. It's a generalized, unstructured, massively parallel, low-mach flow code, and it happens to use Trilinos. These are all of its dependencies. And so for people who haven't seen graphs like this before, this part is Nalu, and these are all the dependencies. And so really, like, the code that you use is based on a whole lot of open source code written by other people. And often building that is more complicated than just getting the code itself built. And that's a simple package. So if you look at other packages like DL2, it's a C++ finite element library. It's even more complicated. It uses, I think Trilinos is in here somewhere. There's PetC, Trilinos, NetCDF, other packages you may be familiar with. But that's even more complicated. And once you get into the data analytics ecosystem like R, things get even worse. So this is RMiner. It's a data mining package for R. This is the actual package here. These are all of its dependencies. This is R, so all of this stuff is built on R, and this is all the native dependencies that you need to build to get RMiner built. And these are the kinds of things that Spack can build for you. So under ECP, there's a whole lot of other complex software. There's 15 plus applications. I think there's 25 different applications in the apps area now. There's 80 software packages, 5-ish different target architectures or platforms. Some of these are dead now, so KNL probably isn't going to be with us much longer. But we still do care about ARM power, NVIDIA, Xeons, laptops. We do care about Windows, although we're not supporting it yet. 7 different compilers across all the different systems, 10-ish programming models, and maybe 2 or 3 versions of each of those packages because of incompatibility. Oh, there's Greg. So that's up to 1.2 million combinations of different ways that we could build all of these things. And so that's unsustainable. It's not really feasible for users to have to pick the configuration that they want to use of those things. They want to rely on something tested, and they would like to have a tool build them something so that they can just say, I want these dependencies, and then go. So each application has its own configuration that it might want. So there are people who do want some control over that. And then developers, users, and facilities, they dedicate a lot of hours to building and porting these things. So most of the HPC facilities I know of have a team devoted to packaging or deploying software, where they basically say, okay, here's the stack we're going to deploy on our system. A lot of them do it manually, and they ensure that all the things that the users need are there when the users get on the machine. But that consumes a lot of time, and it's duplicated effort across these different facilities. And the other thing that people do is they trade reuse and usability for performance. So often this stuff is so complicated to build that people will just stick with what they get working, and they don't bother tuning it. And so I think that's sad. I think you could crowdsource this effort and do a lot better. So one of the goals of Spack is to make it much easier to rely on other people's software. HPC is pretty complicated also because if you think about most industry applications, they'll pick a production environment. So like if I'm deploying a web service in Amazon, I'm probably going to pick an architecture or a type of instance I want to deploy on. I'm going to pick a set of containers that I want to deploy there, and that's my environment, right? It's one configuration for everyone working at my company. In HPC, we sort of have another problem, which is that there are lots of different machines. So is the production environment your user's home directory? We usually deploy things we usually distribute things with source, and so your users actually have to build your application. Is it Livermore, Lanel, Sandia, Argonne, TAC, one of these centers? Those are all very different environments. They have different module names and things. Which MPI implementation is it? All the different centers use a different or a slightly differently tuned MPI. There are different compilers, different dependencies, different versions of dependencies. And so there really isn't a production environment in HPC. There's a bunch of them. And that includes your laptop because people do a lot of their development on their laptops before they scale things up to a supercomputer. So making that whole workflow work is a challenge. So we made Spack to solve this problem. It's a flexible package manager for HPC. It's designed so that you don't have to install it. You go and clone Spack from GitHub like this. So you just say git clone github.com/stack/Spack. You can optionally source a setup script to get Spack in your path and provide some shell support. We'll talk about that later. And then the idea is that from there you can just go and install packages. So you can say Spack install HDF5. It'll find the compilers on your system. It'll build HDF5 and its dependencies after fetching them from the internet. And it'll install them all within the Spack directory. Spack is a little different from other package managers because it allows more flexibility. So you can choose which compiler you want to build with. You can choose which MPI implementation you want to use. You can choose what build options you want to use. It's very general, and so any aspect of the dependency graph that you're building can be customized. And so we provide users handles to do that. It's targeted at a very wide range of users. So we want anyone who wants to use or distribute software for HPC to be able to use Spack. And that includes end users, so people who just want to install an application and run it. That includes HPC application teams. So at the NSA labs, at least, we have very large application teams who may manage tens or hundreds of dependencies for their application specifically. And so they manage all the different environments the application is deployed in. They use Spack to test different combinatorial matrices of all of their dependencies. We want to support package developers, so anyone who wants to get their package out to more people and have them used widely, they can use Spack. And we want to support user support teams, so all those people building the software on big machines that I talked about earlier, we want to make their life easier and automate a lot of it. So since we made Spack in, I guess, 2013, 2014, it's become pretty popular. It's used worldwide. This is really hard to see. Is one of these visible? I guess this one is moderately visible. These are all the places that Spack, where people have hit the documentation site for Spack. And so this is a Spack that reads the docs.io. Basically, the sun does not set on Spack. You can see this effect on our Spack. I stole that from EasyBuild, by the way, because they have a similar map. But okay, so you can see that people are using Spack all over the world in all different time zones. It's pretty focused in the U.S. right now, but you can see that we're actually making some inroads in Europe, Asia, and in Australia as well. There's over 3,000 software packages in Spack right now. There's 1,100 monthly active users. Actually, there's over 2,000 monthly active users on the docs site now in recent months, and over 400 contributors. So it's getting to be, we're leveraging a lot of network effects for Spack to get the software maintained in sort of a crowdsourced way. So this is Spack over time. I guess this is showing, you can't even see that either. You can barely see it here. This is showing active users on our documentation site over time from, I think, July of 2017 through 2019. And you can see that we've had a real uptick in active users on the doc site. So this is where we're breaking 2,000 on the number of active users. And I think the doc site is a pretty representative measure of who's really using the tool. So it's not just people who come by the GitHub site and leave. It's people who are actually reading the documentation. Github Stars, it's a bad metric, but this is useful for comparing to some other HPC tools. You can see up here that this is Singularity, Spack, Chapel, OpenMPI, OpenHPC, and EasyBuild. And Spack is this orange line here. The top one is Singularity, which has gone up really fast. This is Chapel. It's been kind of slow and steady. OpenMPI is pretty big, so we're actually exceeding that. And then EasyBuild and OpenHPC and tools that are mostly targeted at sysadmins, I think, are down here. I think the reason for the uptick here is that we're actually targeting users and developers much more, whereas these folks down here are targeting only sysadmins, so it's a smaller community. Spack's being used on many of the top HPC systems. At Summit, at Oak Ridge, they're using Spack to deploy over 1,300 packages. I think that took them around 2 weeks to build manually before, and they're able to do it overnight in 12 hours now. NERSC is using Spack on Cori, and they're going to be using it on the new Perlmutter machine. And we have some folks from NERSC here, Mario and Tiffany in the back. SuperMUC NG is the big machine at LRZ. That's the biggest non-accelerated supercomputer in the world right now. They're using Spack for deployment. And then recently, Fujitsu and Riken decided that they were going to use Spack for deployment on the upcoming Fugaku machine, which is going to be a big ARM machine at Riken. So we wouldn't be able to do all this without a large community. And I think that's one of the really important things to do when you're building a software deployment system, is to make sure that you're involving a very large community. You can see these two plots. This is lines of code over time in the packages in Spack. So Spack is it's a tool and it's a set of package recipes. And these are the package recipes themselves. And so up until 2015 or so, when we presented this stuff at supercomputing, Spack wasn't very widely used. It was mostly a Livermore tool. And you can see that after that, we started to get contributions from other organizations to the point where at Livermore, we're not even providing most of the contributions for Spack's packages. We're relying on the community to provide those. And actually, we have some pretty stellar contributors. If you look at this graph, you'll notice that the top portion here is Argonne and UIUC. And we also have Argonne in here, and I don't think UIUC is in the top otherwise. This is one person. So this is Adam Stewart, who was an admin at Argonne, and now he's a grad student at UIUC. And so he's been pretty phenomenal for contributing to Spack. And then obviously there are a lot of other organizations contributing as well. In the core tool, I would say it's still mostly Livermore maintained. The Livermore contributions are about half of what's in Spack right now. But we've also gotten some pretty tremendous contributions from EPFL, also from Adam Stewart in the core. And then places like Fermilab and CERN have contributed some major features to Spack because it's gotten some uptake in the high energy physics community. So I like to show these plots because they show that it's not just us. It's actually a really large community of people. And you can go to the Spack GitHub site and click watch, and you'll see that because you'll get a deluge of email from all the things that are going on. So Spack 0.12 is the latest release. It's what we're going to be using today. The major new feature, which we'll cover in the afternoon, is environments. So you may be familiar with virtual environments from things like VirtualEnv and from Conda and other tools. Spack has something kind of like that, but we've tried to unify that with what language-specific package managers are doing, like Rust and JavaScript via Cargo and NPM. There are a lot of other performance improvements and different types of support in the latest release, but the other big change with this one was that we made Spack permissively licensed. And so originally Spack was LGPL, and we had people come to us and say that they were having to ask permission to use Spack because of the license. At different companies and in organizations that are a little stricter about this, they said, we have to go up our management chain and go through our IP office to figure out if we can use Spack. So we said we didn't like that. We wanted to include as many people as possible, so we switched to Apache 2 or MIT. You can pick whichever license you want. And basically what that means is that the contributors to Spack have to they have to provide a patent grant to whatever they're putting in, so you can be sure that anything in Spack is unencumbered. And the users can pick to use it under Apache 2 or MIT. The reason for that is that Apache 2 is incompatible with GPL2, and so having both licenses lets us be used pretty much anywhere, while still requiring the contributors to put a patent assurance as well as a copyright license on what they're giving us. We're not the only tool to automate builds. There are a lot of package managers out there. There are language-specific ones. There are a lot of system-wide package managers. Spack gets its inspiration from the functional package managers like Nix and Geek, if people have heard of those. So the way that we install software and the way that we allow multiple configurations is somewhat based on what's done in Nix and Geek. These are a little different in that they require you to learn a functional language to write the package recipes, and so it can be a little cumbersome for users who are used to a Python insert. The packages in Spack are inspired by Homebrew and Macports. Those are things that I used a lot on my machine, and it sort of, I got frustrated with the fact that I could say install this thing on my laptop, and I couldn't do the same thing on a supercomputer. So the interface is supposed to look kind of like these. And then other tools in the HPC space would be EasyBuild is the main one, and so I would say that Spack and EasyBuild both have pretty large communities now. I think Spack may be slightly larger at this point. It's focused on a different sort of target audience. I would say EasyBuild is very focused on administrators, and they don't have a lot of the flexibility that we offer with Spack. I can talk in more detail with people who want to discuss that offline, but we're going to focus mostly on Spack today. Conda's really popular. It's a binary-only package manager for data science. It's used really widely in the data analytics community, and I would say that, it's a nice model, but it is binary only. So you can't build from source. You can't tune things the way that you can with Spack. You can't get on an HPC machine and experiment with different configurations with Conda. You kind of have to build your packages in advance in the cloud or somewhere else and then provide them as binaries for users. So you really don't have the flexibility or the optimization that you get with Spack builds. We're working on binary support in Spack so that we could actually support optimization in a better way than what Conda currently does. And so I'll talk a little bit about that tomorrow when we talk about deployment in ECP. Right. So on the roadmap, and we'll talk more about these things tomorrow too, we're working on something called Spack Stacks for ECP. We're trying to automate the entire facility deployment process so that you can basically specify your compilers, your MPIs, and say, I want to build a cross product of all of these things. And you can do that in a single file. And we would spit out basically a lock file that says, here's how you can reproduce that whole stack you just built somewhere else. And we're trying to automate basically the entire facility deployment process with a really simple workflow. Better CI support is something that we're working on. We want every site to be able to have a build farm very easily for their Spack packages. So if they want to make binaries, they can do that. I'll talk about that tomorrow in a little more detail. And like I said, we're working on architecture-specific binaries. So we don't want Spack to just have x86-64 is what we build for. We want to build something for, say, Skylake or Haswell or Cannon Lake. And we want you to know that the binary was built for Cannon Lake and that you can reuse it on machines that support that instruction set. And that's particularly important in ecosystems like ARM, where the chips are all kind of slightly different and have weird instructions. And we're working on ways to do that as part of that feature as well. And then finally, we'll talk a little bit more about this, but better concretization and dependency resolution is something that we're working on in Spack. And we'll see what that's about as we go on with the tutorial. So this is the overview of what we're going to cover today. We're up here at the sort of welcome and overview section of the morning. Actually, we're ahead of schedule, which is new. We're going to do some basics on building and linking just to sort of give people background on what it is that you're doing when you make a Spack package. We're going to cover Spack basics. So Greg's going to give an overview of how the interface looks, what it looks like to use Spack. And you can follow along. That's a hands-on session. We're going to stop after that, and I'm going to go over some core Spack concepts. So basically, what's the build model for Spack? What does it look like? How is it modeling dependencies? What do all these commands really mean? Once you sort of have a flavor for what the tool does. And then we're going to talk about configuration a little bit, basically how to customize the way that Spack installs the software that you're doing. After that, we're going to go on to making your own packages. This is hands-on as well, and we'll show you how to make a simple package. And then in the afternoon, after lunch, we're going to come back and talk about things geared towards HPC centers. So basically, building large package installations, generating module files, basically automatically generating the user environment you're used to seeing on HPC machines. We're going to talk about environments, like I said. I think this is a pretty cool session. And then we're going to do some advanced packaging stuff. So the first one is build systems. We're going to go over that a little bit, how Spack supports different build systems and makes it easier to package different things. That's kind of an overview. It's not hands-on. And then we have a packaging section on how to use some of the more complicated libraries in the HPC. So people who've tried building codes with multiple blocks or LAPACK implementations, you know that that can be a train wreck. This is sort of our way of dealing with that. And we'll talk about some of the interfaces we have available for dealing with it at the package level in Spack. And then we'll start, in the last session, we always had some padding in case some of these run over with building your own packages, but we have a lot more hands-on time tomorrow. So we're fairly flexible about this last part. And that's the plan. So any questions on that so far? Okay, great.